Yeah, so constant biclusters are obviously quite specific and not very generic. Yeah? So we just have this one specific value, which is common in the entire submatrix of the data matrix. And the question is, can we somehow generalize that such that it is more general, of course. Yeah, and well, the first idea to generalize that is maybe to still look for constant values, but now not in the entire matrix, in the entire submatrix, but maybe just in all the columns and or in all the rows of the submatrix. Yeah, and that is what is actually coming up here. So here are, first of all, biclusters with constant column values. So we look for constant values in all the participating columns of the bicluster, but in different colors it could be in different columns. Sorry, in different columns it could be different values. Yeah, so the cluster model for those are some additive model here. So we have this specific value mu still existing, but for each column, J are the columns, I are the rows, J are the columns. So for each column, we add some specific bias, so to say, some specific adjustment. So Cj is the adjustment value for column J, and you see that here in the example that we have in the first column. So maybe the constant value here mu is, I don't know, 1, for example, or let it be 0. So the adjustment value for column 1 would be 1, for column 2 it would be 2, and for column 3 we cannot find an adjustment value. So column 3 is not part of the submatrix, yeah, of the cluster. So you see that for all the columns we need, for one column, for all the rows in the same column, we need the same value, a constant value. But over different columns, we may have different values. Yeah? And that is this adjustment value Cj here. And you see the spatial pattern already. It is a kind of axis parallel subspace cluster. So we once again have a kind of spread along these non-relevant features like A3 here. So there is a spread along A3, but in A1 and A2, the two relevant features here, the two participating rows in this bicluster, there the values need to be exactly the same in each row. So we have these 4 points to be, if we project that on the plane A1, A2, all those points are exactly on the same location, yeah? Which is a perfect axis parallel subspace cluster probably. Yeah? And again, we could allow for a little bit variation, for a little bit jitter here among the points, but this is the basic cluster model. Yeah? So let's interpret the whole thing again. So the spatial interpretation is that the points are located on the same values, yeah, but not necessarily on the bisecting line as we had it here in these constant bicluster. It was clear that since all the values need to be the same, it need to be 1 1, 1 2 2, or 3 3, or whatever for A2, the same value for A1. So in all participating columns and rows, we have the same value. Now we have only in per column in all rows the same values, meaning that the points that are located on the same location, if we project it, or if we project them on this hyperplane, on this subspace that is spanned by the columns A1 and A2 in that case, but it need not to be on the bisecting line anymore, because it can be anywhere, because 1 in A1 doesn't mean 1 in A2. It can be anything in A2. Yeah, so that is the perfect subspace cluster that we had before. Now without in the basic model, since we only allow identical values actually in all the columns, the points are actually the same in those subspaces. Yeah, in the visualization with the parallel coordinates, we see that we have identical lines here. They need not to be. So in constant bicluster we had identical constant lines, so the lines were constant here, yeah, and now we have again identical lines, of course, but the lines need not to be constant anymore, yeah, obviously, because they can go up or they can go down, no problem about it. And then in the remaining attributes that are not relevant, there may be an arbitrary spread, of course, yeah. So that is biclusters with constant values, and I told you before that of course we can also do the other way around. We could look for constant row values, and that is the third part here, or the second variant of the second part, actually, the second thing. So this is constant row values, biclusters with constant row values. So the cluster model is the same as before, but we only have now an adjustment value not in the columns but in the rows. Yeah, so you see that for the rows, which are the i's here, not the j's, we have an adjustment value to this specific constant value mu. So Ri is an adjustment value for row I. You see that here we now have, so to say, the other way around than before here. Yeah, here it is constant columns. Now we have constant rows. Yeah, so each point in this or each entry in the submatrix, the rows are constant. The columns, the rows are constant actually. Yeah, and we may have different values in different columns, of course. Yeah. Okay, so the result is actually points that building a sparse hyperplane parallel to the irrelevant axis. You see that here. So the points have actually are on a hyperplane which is parallel to the irrelevant attribute. The irrelevant attribute here is A3. So we have some specific hyperplane here where the points are embedded in a two-dimensional hyperplane in that case, which is parallel to A3. Yeah, so it has a couple of degrees of freedom, of course, but that's how it is. Yeah, so it's again quite similar to access parallel subspace clusters, and we'll see that on the next slide. The spatial interpretation is that if we project the points on the participating columns, we'll see that the points are located on the bisecting line of the participating attributes. Yeah, so you see that if we just project, so if we consider also A3, those points may have an arbitrary variation, an arbitrary spread along A3, but they are all again on this bisecting hyperplane here, which has some arbitrary extent in the direction of A3. Yeah? But if you project them on A2, A1, the participating columns, then you see that they are all located on the bisecting plane. Why is that the case? Well, they have to be, well, if A1 is 1, then A2 has to be 1, 2. If A1 is 2, then A2 has to be 2, 2. Yeah, that's the model of the cluster, obviously. Yeah, so and that is something which is a kind of model for some subspace clustering, obviously. Again, yeah. Sorry. And if we have a look at the parallel coordinates here, then the specific pattern that we see in this parallel coordinate plot is parallel constant lines, rather than these identical lines here, which are parallel again, of course, well, because they're identical, of course. Then we have here parallel lines, but they need not to be identical anymore, because you see that the parallel line can be at different values, so to say. And again, of course, in these non-relevant columns like A3 here, we have an arbitrary spread, of course, of the values. Yeah? So that is the specific pattern in the parallel coordinates for constant rows. Yeah, so next up will be the third part, which is constant coherent values.